Okay, so what we did so far was a mass attached to an oscillator to a spring, and we considered the case where there was no friction between the mass and the surface. So for the frictionless surface system, this equation describes the system. And how did we get this equation? We got from the only force acting on this was the spring force. Okay. Now, if you want to add friction, so you have to add an additional force. Okay. And here's how we model this. So now here's a simple way to add friction. You take this mass, and instead of it oscillating in air where the friction is almost negligible, make it oscillate in a bath, oil bath, and there'll be friction there. Okay. Now it turns out that if the object is large, to a good approximation, the friction depends on how fast you're going. Okay. And the simplest way we'll model is this is the following. Okay, so the friction force will be a constant and proportional to the velocity. What does the minus sign tell you? So if you're moving in that direction, the friction force is in the opposite direction. Okay, so the friction force is always opposite to the direction in which you're moving. Okay. So now what we want to do is, so going back, now our next model, so this was first iteration, and now we're wearing bigger boots. What are we going to do? We're going to throw in friction. Okay. So now there are two forces acting on the object. Okay. The two forces acting on the object are, so the net force equal to mass times acceleration. Acceleration is d square x t by dt square. The two forces acting are the force of the spring and the friction force. Okay. All right, minus kx minus b. What is v? dx by dt. So there is your new differential equation. It was that simple. You threw in friction. Okay. So let's look at that. So the friction force, it's also called a drag force. If it's in a fluid, the drag force is modeled by that. B is called the damping force, and you'll see that this is important. Okay. We'll talk about applications. Okay. So now the net force is the force acting on the system is the spring force and the friction force. Okay, so there's your mass times acceleration is the spring force and the friction force. All right, so now you're solving a more complicated expression. Without the friction, it was just this term and this term. With friction present, you added this new term. And now you're learning to solve a little more complicated equation. But here's the neat thing about it. If you want to get the frictionless case, what do? Huh?
B equals 0.
Very good, David. So that frictionless case is a subset of this equation. Okay? So here you're solving this more complicated equation, and if you're tired of friction, just make that 0. B equal to 0, and you get the frictionless case back. Okay? All right. Well, Okay, let's solve this equation. And again, you learn various tricks to solve the equation in the differential equation class. And here is the solution. Okay, you see that B, that friction constant, the friction coefficient, is only coming in there. What it's doing is it's killing the amplitude. It's making the amplitude go to 0 over time. And that's what this diagram is showing you. You see the amplitude of oscillation is going to 0. Okay? So if you have friction present, you pull that mass to the side, and eventually the oscillations will die out. And that's what we are showing you. And the oscillations die out exponentially. Okay? Smaller B is, slower the oscillations will die. If B is 0, this is 1, and the oscillations won't die. It'll just keep oscillating forever. Okay? So there you go. We modeled friction in. Okay? And we'll remember that, so it'll be important, like I said, in a little bit. Okay. So with friction present, actually the frequency also changes. So this would be the frequency without friction. Okay, so the new frequency is the old frequency. This is the frequency without friction, is K over M. Okay, so that was the angular frequency. So this is the old frequency. And so with friction present, the new frequency is slightly smaller, and that makes sense. If there was no friction, it would be oscillating fast, and then we add friction, so it's oscillating a little slower. Okay? So the friction has reduced your oscillation frequency. All right, so this sort of stuff is important because, we incorporate this in all our devices. Okay, so that's what shock absorbers are. Okay, so your wheel is essentially a mass attached to a spring. And now let's say you're riding your motorbike and you hit a pothole. Okay, so if you hit a pothole, so this is your wheel attached to a spring, it'll keep oscillating. And after you come out of the pothole, you don't want your wheel to be bumping on the highway. What do you want to do? You want to kill those oscillations. How do you kill those oscillations? By putting a damper. And what is the damper? The damper is the oil in the shock absorbers. Okay. All right, so this is what this says. Okay, so depending on how large this constant is, okay, so if this constant is equal to that, then this frequency of oscillation is 0. That it won't oscillate. Okay, so if this constant is such that it's less than that, then the wheel will oscillate. If this value is exactly equal to that, the system won't oscillate and it'll just come back to its equilibrium position. Yeah? And if this is too large and this is negative, the system won't even come back to its original position. And you don't want your wheel not to come back to the road. Okay? So you want to make sure that it is just slightly below that. So it'll come back to the road. You'll make sure that it comes back to the road and it'll oscillate just a bit. Okay? So this is called critical damping. When this is equal to that, that's critical damping, and the system won't oscillate. And you want to damp your system in many cases. Okay? And again, I'll show you other systems. Okay? All right, so we studied a system without friction, and then we became braver and added friction to the system. Okay, what did friction do? It slows down the oscillation. Okay, I don't know if you've ever done this. So there's a child in a swing at a park, there's friction, and as the swing slows down, what happens? The child starts crying. And so, to make the child happy, what do you have to do? You got to keep pushing. So now we'll add that. Okay. So now we'll look at an oscillating system with friction. Now we'll add a driving force. Okay. So there is the third system we'll consider. Okay. So here's d square mass times acceleration. That's equal to the sum of all the forces acting on the system. Okay. So minus kx, what is that? What force is that?
Spring.
That's the spring force. What is this force? That's the friction. And now we'll add okay, so here's the amplitude of the driving force, the subscript D telling you a driving force, and here's the driving frequency, and we'll add an oscillating force. Okay? So this will be the driving force we'll add. Okay? So that's the third kind of system. So forced oscillations. Okay? So there's the driving force, there is the friction force, there is the spring force, and there is your mass times acceleration. Okay? So we've progressively gone from a simple system. This was the system we started off with. Then we added this term. We made it that much more complicated. And now all we're doing is keep adding terms. You know? So as we are just building your expertise. Okay? If you get tired of all of this, just make this 0 and this 0. Okay? And you get back your original system. Okay? So your original system, see, this is a subset of that, this is a subset of that, and so on. Okay? All right, so now the solution of this is a little more complicated. Okay? So here's the solution. Now the amplitude, what is this saying? The amplitude depends on the driving frequency and the frequency of oscillation with friction present. Okay? And the system is oscillating at the driving frequency, at the driven frequency. Okay? The child oscillates with the frequency that you're pushing at. It doesn't oscillate with the natural frequency. Okay? All right. We'll give you an expression for this guy. All right, so here's the amplitude. So here's the amplitude as a function of the driving frequency and the frequency of oscillation of the system is equal to, here's the amplitude of the driving force, there's the mass of the system, here's the driving frequency, here's the natural frequency. What is B? Yeah, so the friction coefficient, here's the driving frequency, and so on. All right, let's look at this equation. This is the amplitude of the oscillation. The amplitude of oscillation is that. Okay? Now let's look at this. If this term is small, okay, let's say this term is small, and let's say the driving frequency matches the frequency of oscillation, this term becomes 0. And if this term is small, then this amplitude of oscillation can get large. That's what this is showing you. See, for smaller and smaller friction, smaller and smaller B, when the driving frequency matches the natural frequency, see that is 1, you see the amplitude of oscillation is getting larger. Okay. Well, what does all this mean? Okay, let me show you what this means. This means you should be scared. Okay, so here is a system. In this Omega is the driving frequency and omega naught is R omega. That's the natural frequency of oscillation. You see, when the driving frequency does not match the natural frequency, that's the situation. And here's the driving. So what we're going to do is we're going to take a mass attached to a spring, and we are going to hold on to the spring at the top and drive like that. Okay? So that's equivalent to you pushing a child on a swing. Okay? Right now, you're pushing the child randomly. When the driving frequency doesn't match the natural frequency, you're pushing the child randomly, and of course the child won't go too far up. Only when you push at the right time will the child go, the swing amplitude will increase. Okay, so now let's start this. Okay, so you see there's the driving frequency. The driving amplitude is given by that arrow, and you see, so the amplitude of oscillation doesn't change much. Okay, nothing spectacular is happening. Okay, now what I've done is, see, now the driving frequency is very close to the natural frequency. Again, I'm just doing the same thing. I'm holding on to the spring and just giving the same amplitude, except that my driving frequency matches the natural frequency of oscillator. Now you're setting up large amplitude oscillations. Well, why do we care about this? Okay, here's why we care about this. This driving frequency could be a wind, and this could be a bridge. If a wind somehow is exerting a force whose frequency matches the natural frequency of the structure, you can destroy the structure. And this is not just theory. You've seen this, I'm sure you've seen this plenty of times.
Hey, it's me.
You don't even realize. I'm already inside. I'm learning how you speak. I just need to become.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
All right, so for every large structure, you have to put dampers in. Okay, what you have to make sure is that you have enough damping, that this damping coefficient is large enough where when a driving frequency matches the natural frequency of the structure, you don't get runaway oscillations. Okay. If the damping is too small, then you get large amplitude oscillations. Okay. So for every large structure, you have to do that. Here's a building in Philadelphia. What is the damper? At the top, you have this water tank. Okay. As the building sways in this direction, the water is not solidly attached. There's a delay. The water doesn't come over there. As this thing is oscillating, the water is oscillating in the opposite direction, and it's providing friction. So all tall structures have these dampers attached to them. Every bridge, you can go to these bridges here, and they have dampers. Okay, I'll come back to the Tacoma Narrow Bridge in a second. Here's the Burj Khalifa. At the very top, okay, that's the top floor is the most expensive floor to rent. But here's the problem. See, the top floor can sway up to 2 meters at the very top. So here's a meter. Here's 2 meters. At the very top, that floor sways that much. It could sway that much. You want to build it so that the windows don't pop out. You want to pay millions of dollars of rent and feel nauseated? No, right? You don't want your hot coffee spilling on your lap, do you? All right, so you have to make sure that you have enough dampers. All right, so here was what was happening at the Tacoma Narrows Bridge. What was happening? So here's a top. So this is the top view of the bridge, and these are the piers underneath, or the pillars. Okay, so wind was blowing like that, and then vortices would break away from the. Okay, so this is one of the explanations. Vortices would break away from the pier at a frequency that matched the natural frequency. So this was the driving frequency, and this was the natural frequency of the bridge. And so when this frequency matched that frequency, you set up large amplitude oscillations. Okay? And this bridge didn't have strong enough dampers, so it collapsed. So you heard in the movie, this was the third largest longest suspension bridge at the time. And it collapsed within a year. Now, you would think that, so we've learned to add dampers and stuff like that, but there are situations when you can't take into account. They built a walking bridge in London across the Thames. This was recently, about 10 years ago. In fact, a friend of mine, his dad was an engineer there. And so the first day, about 3,000 people got on the bridge, were walking, and it set up oscillations. So they had to close down the bridge for 2 years, add additional dampers and stuff like that. So this stuff happens. Okay. All right. So in Mexico City, there was an earthquake about 250 miles from Mexico City. Okay. And here's what happened. So here's Mexico City. Okay. It turns out that the natural frequency of oscillation of a building is related to its height. Okay. So here's the earthquake, and these earthquake waves traveled here. And the ground was shaking at a frequency of 3 radians per second. Okay, so in a circle there are 2 pi radians, which is about 6 radians. Okay, so the ground was shaking, the period was 2 seconds. Every 2 seconds you had one oscillation. So that's how the ground was shaking. And it turned out that the frequency of this matched the ground frequency, and all these buildings collapsed. These guys, their frequency didn't match the ground frequency, and they were fine. Okay, so resonance is a scary phenomenon. Okay, when a driving frequency matches the natural frequency of oscillation of a structure, you can set up large amplitude oscillations. You've heard of singers breaking wine glasses with their voice? That's what that is. Okay. I can potentially break this table if I can figure out the natural frequency of the table and then I drive at that frequency. Okay? All I have to do is this and I can break the table. All right. So you have to be aware of this kind of stuff. All right.